Okay, thanks a lot for coming, and it's really my great pleasure to be at this conference. It's not my usual topic of conference, but I will try my best to fit into the themes of this conference. You'll see some little bit of a renormalization, visualization. There will just be drawings. Geometry, number theory actually will appear in one of the proofs, but it will really be the number theory for babies. But unfortunately, with dynamics, I really didn't manage to fit it into. But I would wish maybe some dynamics would be interested in talking, and they're definitely interested in one may try to do. So this is joint work with Dragomir Saric from CUNY and Catherine Wolfram, who's graduating from MIT this year. The main objects we'll be talking about would be this universal Teichmann space. It's also infinite dimensional, but for a different reason than Frederica's Teichmann space that she was looking. But this is just modeled by the collection of all quasi-symmetric homeomorphisms of the circle. Modulo, I put the modulo on the left, modulo Möbius transformations. Or if you like, I would just take a quasi-symmetric homeomorphism which fixes 3 points on the circle. So this is called universal Teichmann space because first of all, it is a complex Banach manifold. You can still talk about Bayes embedding. So one has the same complex structure as what you know from the other finite dimensional Teichmann spaces. And moreover, all the Teichmann space of hyperbolic surfaces, they embed holomorphically into this universal Teichmann space. And this is infinite dimensional since you know any genus G Teichmann space has to be embedded into it, so already you cannot have any bound on the dimension. Also, from the definition, you can see that quasi-symmetric homeomorphism, you can tweak it around a lot. Okay, just to remind you what quasi-symmetric means, it just means that if you take arbitrary 3 points on the circle with the same distance, the image under it won't be necessarily equidistant, but their distance between the 2 points, their ratio will be bounded uniformly from above and below. Or it can be defined as a set of quasi-symmetric homeomorphism, where all quasi-symmetric homeomorphisms can extend to a quasi-conformal homeomorphism of the disk, and mu, I always denote mu by their complex dilatation, and its subnorm is strictly less than 1. Okay, for classical Teichmann theory, you know that we can talk about Teichmann distance, Weil-Petersson metric, and also Weil-Petersson metric. Here on the universal Teichmann space, you can still talk about Teichmann metric, but that's a Finster metric. It's not really a Riemannian metric there. But still, we like Weil-Petersson metric. And also in compact surface for the Weil-Petersson metric has such a nice magical formula, can be written in French-Nielsen coordinate. Right? It doesn't depend on which Pence decomposition, they all look the same. And they look very simple. And then we ask a question, what can you do for universal Teichmann space? Can I find the countable bases which are going to mimic the French-Nielsen coordinate? Okay, this is one goal of this talk. The second one is that since it's an infinite dimensional space, there has a lot of subspace which will be interesting. It might not be the case for other finite dimensional Teichmann space, but here, since it's infinite dimensional, one can talk about convergence problem and how you take whether subspace is complete and such kind of things, and also the question how one can put a Weil-Petersson metric on this universal Teichmann space. So we are going to try to understand these subspaces in terms of the new, not new actually, the coordinate system I'm going to describe. So the coordinate system is actually known already from Dragomir Saric's work, but let me just explain it slowly. So since we consider a universal Teichmann space, which is quasi-symmetric homeomorphism fixing 3 points, so let me just mark these 3 points, -1, 1, and I on the circle. I want to create a coordinates which has maximum symmetries. Okay, let's just look at the fairy tessellation. What you do is that you look at your triangle and you keep reflecting across the edges. Right, this is the Fourier tessellation I get. This is a triangle, and here on the red, I just drew the a dual tree. This is a combinatorial object. It's a three-valent tree. And I can also map the unit disk to the upper half plane, like sending 1 to infinity. All these arcs, they're just becoming these vertical lines. And -1 to 0, and I to -1. And the rest of the other triangle here, they're just by index. These one are indexed by integer numbers, and the other vertices, they're going to cover all the rational numbers. And in fact, so this is something called a freshman sum. Let's say if I look at this, what is the descendant of this edge? So what is the edge connecting 0 and the 1/2? Well, you just add up the numerator and the denominator. You get the vertices of the this inside. So the edge, all the vertices, they're given by rational numbers and infinity, and the edge is inside. All the vertices are represented by these rational numbers. And it is inside the edge if and only if the determinant of this 2x2 matrix is 1. And then you can see that there's also the PSL2Z action on the right. Shear coordinates is going to encode the circle homeomorphism into a number, so as a family of numbers on the edge. So now I look at this tessellation and apply this homeomorphism, and it sends the vertices to some other vertices, and I connect them again by hyperbolic geodesic. And now these triangles, they're not anymore symmetric to each other. And there's a shear, which is telling you how much, like say this point, is sheared away from being just below, with from -I. And here it's measured using maybe you can use this way. You just draw the normal starting from this point to this edge in the middle, and you draw the normal from here. And the shear coordinate is just the hyperbolic length about this arrow. And the shear can be positive or negative. Positive if I shear to the right, and negative if I shear to the left. So it's not exactly the earthquake, because earthquake you only allow one direction. So here I would allow both direction shears. And I can also describe intrinsically just using a cross ratio. I just look at the image of these 4 points. I say, I wonder what is the shear along the middle edge. I will look at the cross ratio starting from one of the endpoint and take a log of the cross ratio. It actually doesn't matter if you start from this point or start from this point. It will give you the same number. So the edges I consider, they're not oriented. In the upper half plane, it may be easier. So here, let's say, just say this quad. So these 3 points still map to -1, 0, infinity. And the last one will just be mapped to exponential the shear, which is here. Right, so here, if you draw the normal, here it lands at I. Here, if you draw the normal, it lands exponential s times I, and the hyperbolic lands exactly s. So the shear actually, they're very nicely encoded in the upper half plane. So the shear tells you what is the ratio between the widths of these two bands. Right, here the ratio is exponential, the shear in the middle. So the width of this band, it will just be the shear along this edge. So the width of this band is given by exponential of shear along this edge plus this edge. All right. Okay. So now from a circle homeomorphism, I get this family of shears. On each edge, I can record what is the shear along each. And you can definitely reconstruct the homeomorphism from the shear. Well, you just do like I can develop each edge. If I read off what is the shear here, it will tell me where this point is. And then I read what is the shear here, it tells me what the point, next one. So you can iteratively it tells you what is the map on the vertices. But it may not be a homeomorphism because the image of the vertices may not be dense. As here, I'm just taking one fan. Okay, in terms of name, by fan, I just mean all the edges coming out from one vertices. If you just look at the image of one fan, like on this vertical line, I can choose the shear such that the vertical line accumulates. So it's going to leave a part which is, won't be visited. Okay, this may not be dense, but Dragomir has actually given equivalent condition on shears for the image of V to be dense. It's a little bit complicated to describe here, but it's not going to be important here, but it's essentially describing the fact this image of vertices are dense. Okay, at this point, to me, actually, I'm happy. When I see the shear can give me something which is not homeomorphism. Because when we study universal Teichmann space, you always stay inside the space of a quasi-symmetric homeomorphism. I'm originally a probabilist, and in probability, we study random objects. And these random objects are usually much more rougher than quasi-symmetric quasi-circles. And for instance, in the simulation that you see from John's talk, he has shown this critical easing where you see the clusters, the critical easing, they're scale invariant. The picture at they're actually more than scale invariant, but they are also conformally invariant. Even you rotate it, you don't see the lattice from there. And so for instance, the objects we would consider is also the boundaries of those clusters, and they're much rougher than quasi-circles. They're actually called SLE curves. So here, like if we have a system of coordinates which can even give me things which are not homeomorphisms, and it means that it can go much out of the space of quasi-symmetric homeomorphism. So that was actually the original motivation. But I'm not going to talk more about probability here. Okay, one natural question is, once we can characterize a homeomorphism, can we characterize quasi-symmetric homeomorphism? The answer is yes. So this is the equivalent definition that Dragomir gave. It says a shear coordinate is induced from quasi-symmetric homeomorphism if and only if there exists a positive number m such that no matter which edge that you take in the Ferry tessellation, so I will take this Ferry tessellation and call it E naught, and I look at the fan, one of the fan that contain this edge, and I send this fan to these vertical lines. Okay, for each edge I can do such a thing. And it's quasi-symmetric if and only if no matter which edge you take as a center edge, and then any positive integer k you take, and you look at k interval to the left and k interval to the right. So this is the tessellation of the image of the Ferry under this phi. And the condition is that the ratio in between these two intervals, they're bounded above and below by m. It's clear this is a necessary condition because we are asking only about some information about discrete sets, and this is exactly the same characterization for quasi-symmetric homeomorphism if you allow the points to be arbitrary equidistant. But here what he shows that actually you only need to check for this countable set. And this length here, they can all be written in terms of shears. So this is the one condition that he gave on quasi-symmetric in terms of shears. And more interestingly, one can also talk about infinitesimal shears. So this will give you tangent space of the universal Teichmann space. And the Teichmann space, they're given by Zygmund vector field. And so these are conditions about how the vector field, some regularity of the vector field. And this condition on the Zygmund vector field would just be the condition for the shear, but you take its infinitesimal form. You take derivative in that, it will give you the condition here. And actually, this is quite amazing because one actually can also ask the same question: can one characterize the Zygmund vector field in terms of Fourier series? The answer is not no, but here in the shears, it's actually pretty easy. So maybe this is another reason to promote this shear coordinate for describing circle homeomorphisms. Okay, maybe let me just pause. Is there questions about like the definition, how shear coordinates? Okay, then I was going to talk about a subspace of it, it's called the Weil-Petersson universal Teichmann space. Remember, universal Teichmann space is only the Teichmann metric on there is just a Fink's-Slur, and you cannot talk about Riemannian metric there. But if we want to say French-Nielsen, or you want to say things like symplectic form, it's better to have some Hilbert manifold structure. Right? It's infinite dimensional. It's not clear how you define L2 on it. Well, one natural definition is that let's look at all the circle homeomorphism whose Beltrami differential is L2 integrable. All right, this is a subspace of the universal Teichmann space. All right, this is one definition of it. So Taktajan and Theo, in their seminal work from early 2000, they show that, T01 is another name for WP. So they're exactly the same thing. They say that this Weil-Petersson universal Teichmann space is actually has a unique right invariant Kähler metric. So already, since it's subspace of T1, we can actually show that its complex structure also restrict to WP. And here, okay, so they also show that this is WP is a topological group for the metric, for this Kähler metric that they define. And so here, the reason saying that this space has a unique right invariant Kähler metric is referred to, if you think this as this homogeneous space, so Weil-Petersson homomorphism mode Möbius transformations, you have the right action by itself. And if you ask for this metric to be Kähler and also right invariant, there are actually not so many choices. There's actually one choice to define such a Kähler metric. The only degree freedom would be just putting a multiple. You can take a multiple of that. And so this is actually already studied in the 80s by string theorists. They were looking at the diffeomorphisms, C infinity diffeomorphisms. They don't care about convergence issue. And they can already see that there's a unique way to put a Kähler metric on the space. And what Takta and Theo they did is to really make this rigorous and giving you how you model on Hilbert spaces and how does the metric look like, etc. And Takta and Theo they also show that this Kähler metric is actually also Kähler-Einstein. Again, surprising, because it's an infinite dimensional space. When you talk about Ricci curvature, you have to take an infinite trace. And Takta and Theo they show that in this case you don't need even to regularize. The trace is well defined, and they show that the Ricci curvature is proportional to the Kähler metric. And this is not the case for finite dimensional Teichmann space. They are Kähler, but they're not Kähler-Einstein. And this Teichmann space is also complete. It's connected and complete. It's a very nice space. And this is the space on which you can talk about Riemannian metric. You can take so Kähler here means you have a Riemannian metric and a symplectic form which is compatible with the complex structure. Right. And one can be also more concrete and just say, okay, it's how we characterize analytically these homeomorphisms. There's a work by Shen in 2013. They show that phi is Weil-Petersson if and only if log of phi prime is in H1/2, this Sobolev space H1/2. Just to say what this means, it just means that this function has finite Sobolev norm, and Sobolev norm can be explicitly written this way, in this H1/2 space. This is also if and only if characterization. Well, so for analysts, why just forget about all Taylor geometry and we can just work with this space. Function for which have certain integrability and differentiability, right? This H1/2 space. Maybe an example, if you know log of phi prime is in C alpha, so this is like I say, if phi is C1 alpha, C1 alpha just means phi prime is C alpha. And actually, I would take the definition for C1 alpha for being log of phi prime is C1 alpha, is C alpha, sorry. So if log of phi prime is C alpha, where alpha is strictly larger than 2, then you can check the right-hand side is finite. Right? Here you would have 2 alpha here and divided by s minus t squared. So it will be double integrals. So this is the largest holder class, which is inside Weil-Petersson. Just to get the feeling of what is Weil-Petersson. Yeah, this is the largest holder class. And the C1 1/2, if alpha is 1/2, this is not in Weil-Petersson. Maybe I would just record this on the board. Okay, maybe C1 alpha is in Weil-Petersson if and only if alpha is strictly larger than 1/2. All right, so here I just show you 2 definitions of this Weil-Petersson universal Teichmann space. There are actually tons of equivalent description. It's still very active, and like there are links to hyperbolic free manifolds. There are links to operators, certain operator called Gronsky operators, Hilbert-Schmidt, if and only if this homeomorphism Weil-Petersson. So there are really tons of equivalent description. Yeah. Okay, so this is the space that we're interested in the most. So this is a place we can do all the geometry. There are links to probability theory, like the curve, the SLE3 curve that John was showing. But this is a topic of another talk. We ask, can we characterize Weil-Petersson using shears? Or we can ask, what are natural L2 subspace of shears? Okay, let's try to tackle the second one first. We can have some naive guess. We can take L2 shears, for instance. Let's just take all the shears for which is L2 summable. But unfortunately, if you only know the shears L2, it doesn't even imply this is a homeomorphism. And here is one example. You can probably leave it as an exercise. If I take just shears which is non-zero along inside one fan, and inside this fan only for n larger than 1, and you can compute what is the width of each, and you can see that they sum up to something finite. So it's not a very good space. It's too large. Okay. So then we decide to take one step back and say, let's just look at finite support shears first. Here I drew one, this blue, I hope you can see the blue color here. They just represent the places where shear is non-zero. At least a subset of it will be non-zero. Outside will be 0. We have the following lemma. So if the shear has finite support, then in my developing algorithm, at some point I will just stop shearing. So what I get is the circle homeomorphism. This will be piecewise Möbius outside of the vertices of the support. And in this case, if you have piecewise Möbius homeomorphism, there are C infinity on pieces, so the only difference can happen is that whether the derivative matches on the edges or not, on the vertices or not. So if the derivative doesn't match, they won't be Weil-Petersson because if they have a jump in the derivative, this h1, they won't be h1 half. So here we know it's easy to check actually the phi in this piecewise Möbius case. When phi is Weil-Petersson, if and only if phi is C1, if it's C1, it will imply the C11 as well. Möbius transformation is C11. But also in terms of shear, it just means they're balanced, meaning that they always sum up to 0 on all the vertices. This is really just a straightforward check. What are the Möbius maps on the different pieces? Okay. So this is the finite balance condition. Okay. What is the smallest finite balance condition? This is called what we call the diamond shear. Well, the diamond shear, these are like 4 shears. They were in the form 1, minus 1, 1, minus 1. They sum up to 0 over the vertices. And we call this 1 unit of diamond shear, and I will represent it as the diamond shear on the dual tree. So I will just, terminology, I call this diamond shear supported, a unit diamond shear supported on this edge, or this dual edge, for being like 4 shears in this order. Simple lemma, any balanced shear, finite balanced shear, is a finite linear combination of diamond shears. It's really a basis for balanced shears. To prove of it, okay, I'm just going to show you pictures, how you do it. This is my support of my shears, which is non-zero. I'm going to write them in terms of diamond shears. Well, the first step, I will take the convex hull of this shear. The convex hull just means that here we have a well-ordered ordering on this triangle. I will call this, say this edge as the generation 0, this generation 1, generation 1. There's a generation well-defined on this Ferri tessellation. And I will just connect all the edges to the lowest generation. So, and I'm filling all the edges inside it. It's finite still, right? And now for each, so now this is the union of the blue triangles, and the dual vertex are these points. I also mark them, and now I connect them together. They form a tree, the orange tree, right? And now I pick a leaf. Well, for this leaf, I know that this only has 1 point, so this triangle only has 2 edges, which is connecting. So this vertex only has 2 edges, which has non-zero shear. Because it's balanced, I know what is the diamond shear. I need to put, in order to remove the diamond so that this is becoming 0. Right, say if the shear is minus alpha plus alpha here, then I know I should put my alpha, my diamond shear to be alpha on this edge. So I will just do this iteratively. Once I decide what is the diamond shear on this edge, I just remove it. The remaining configuration is still balanced. I'm only removing balanced 1 diamond. So keep iterating. This completes the proof. One can also show that if there's only one way to construct such a diamond shear. Okay. Also, if we know what is a diamond shear, so theta I would denote by theta, this is a diamond shear coordinate. Okay, so 1 diamond shear here corresponding to 4 shears on the diamond around it. So this is a function. Sometimes I write this just from E to R. You can also write E star to R from dual tree, but they're like on one-to-one correspondence. So I'm going to be sloppy on that. So from the diamond shear, we can recover the shears very easily. Well, if I want to know what is the shear on this blue edge, I just need to read what are the diamond shear on the 4 edges. They're the only diamond shear going to contribute shears to the middle. That's such a simple relation. But now our second guess for the nice L2 space is called this H space. These are the shears coming from L2 diamond shears. Right, now the diamond shear is infinite support, but since the shear is only a simple function of the finite sum of theta, it's well defined. Okay, this is my collection of shears I'm going to consider. This is the L2 diamond shears. So our mean theorem says that, I will copy it here. We have C1 alpha of S1 being strictly inside H, which is strictly inside Weil-Petersson, which is also strictly inside this L2 shears for any alpha which is 1/2. So this result is sharp because you cannot take alpha to be smaller since it won't be in WP. So in some sense, it's saying that this space in the middle is quite close to Weil-Petersson, but unfortunately, they are not exactly the same. All right. So this is the mean theorem. Maybe before, so I was going to tell you what the French-Nielsen coordinate here. But before that, let me just say, what does the diamond shear actually doing? Okay, this combinatorial definition, the shear can be written as 4 sums of diamond shear, but the diamond shear can also be written as some combinatorial information of shears. But there will be an infinite sum of shears. I'm not going to write it, but if we have a shear coming from this H space, then this S will satisfy the infinite balance condition, which means you can take the infinite sum along each fan, and the sum will be 0. And the limit exists, you go to the left, the limit exists, go to the right, the limit also exists. And the bi-infinite sum on each fan will be 0. And this condition will force my circle homeomorphism to be, first of all, if I take a shear like this, it will actually induce a quasi-symmetric homeomorphism. We check this using Dragomir's condition. But more importantly, that this infinite balance condition would tell me that this homeomorphism will be differentiable at all the rational points. And this combinatorial, so this is, shear can be expressed as combinatorial information of shears. Diamond shear can be expressed in terms of shears. And this will be, we can prove that diamond shear along one edge is simply given by this formula. So let me just copy it here. Okay, theta of an edge, A, B are the endpoint of the edge, will be 1/2 log of phi prime of A, phi prime of B, minus log of phi A minus phi B over A minus B. So this is coming from the combinatorial, some combinatorial consideration. I'm not going to give you the proof. But if you just look at this formula, if my phi fixes 2 endpoints, if phi fix A, phi fix B, then this term will be 0. What you see is to the homeomorphism, how it dilates near an endpoint of my edge. And actually, the additional term is such that the diamond shear is defined, it doesn't change if you post-compose your phi by a Mathématiques transformation. So from this formula, we can finally give a geometric description of theta. It is related to the log lambda length of Penner. Well, I've prepared my picture here. So for the Ferri tessellation, you saw already in Kurt's talk that there is a nice circle packing. You can draw this horocycle, which are they're tangent to each other if there's an edge connecting the endpoints. And in the upper half plane, the horocycle above the rational number p over q, the diameter is just 1 over q squared. Right. And so now if I have a circle homeomorphism, I will just draw two endpoint. And this is my A, this is my B. Originally, they have this horocycle which is tangent to each other in Ferri. I have a phi. There's a natural way to change the size of the horocycle. So say if phi sends A to here, phi of A sends B here, phi of B. And phi is differentiable at A and B. One can take a Möbius transformation which has phi of A. So this Möbius transformation A equals phi of A, and Möbius transformation of its derivative equals to phi prime of A. It's not unique, but all the other differ by parabolic element. And now this horocycle will be we just take this one as A of the horocycle. Say the C of A, this is A of C of A. Right, this horocycle, it changes, only depends on the information of phi, what's going on at A. So they have nothing to do with what's going on at B, so they don't necessary to be matching anymore, tangent anymore. So they changes the different size. And what is theta? Theta, now you can draw the geodesic in between. The length in between these two horocycles is called theta of E. Sorry, the lengths are, let me should write this. It's not exactly. So theta of E is minus 1/2 of the length of this thing in between. Okay, you can see this. If we take the case where phi fixes A and B, the derivative, if the derivative is smaller than 1, they will going to shrink these two horocycles, and the distance, the space it leaves in between, is given by just the log of the product of derivative. Okay, in this sense, we can interpret this theta as kind of a renormalize the length of the geodesic. Right, I have a Ferri tessellation. They started with all the lengths to be 0 because they're all tangent. I apply a circle homeomorphism. It changed my tessellation to some other way, and I'm now measuring how long this geodesic by using the same normalization to truncate the length of the geodesic. So the theta is just a renormalized length of this geodesic. And this has been studied by Penner, and he called it the log lambda length. We only discovered this relation later. We didn't change to log lambda length. Okay. So the funny thing that I promised, it follows actually easily from a calculation of Bob Penner. He shows that the Weil-Petersson symplectic form on H, now H is inside WP after our result. we can talk about this tangent space. And we can look at its symplectic form, induced from Weil-Petersson Teichmann space. And it's actually very, very simple. The symplectic form is given like this. You sum over all the shears and look at how the theta, this is minus 1/2 the length, changes. How much the shear, this is like the twist. This symplectic form just looks like this.
This really looks like Wolpert's kind of magic.
Yeah, and the proof of Penner, what he does is he takes 2 log lambda lengths, so 2 theta, and look at their symplectic form by these two, and it's a brute force calculation. That I asked Bob, he also, yeah, he was very puzzled. Yeah, but I find this really amazing. But here, actually, it's a little bit different. Right? Okay, so here the theta, they has a combinatorial relation to the shears. So they're not independent coordinates. And here we take the space to be H. This is, I recall you, those are the place where the diamond shear is L2. If you know diamond shear is L2, since shear is just the sum of 4 diamond shears, you also get the shear is L2. So everything is convergent. You can, yeah. Yeah, so it's well defined at least. Okay.
Can I just make a comment?
Yeah.
So, I mean, not everybody knows the finite dimensional version of this statement. It might be nice to.
Okay, yes. Finite dimensional would be Weil-Petersson. There would be sum of 1, 2, 3g minus 3 of, I think, minus 1/2 exactly the L I wedge d tau I, where Li tau I, there's a French-O'Neilson coordinate coming from Pann's decomposition. Li is the length of the geodesic, and tau is the twist. So even the constant here, minus 1/2, is the same. And maybe it's also, let me write down in terms of, in Weil-Petersson, the other definition of Weil-Petersson symplectic form in terms of harmonic Beltrami. So mu, I like to put the dot to say this is an infinitesimal. They're harmonic Beltrami on disk. This is equal to imaginary part of integral over d mu dot hyperbolic metric here. Yeah, so for the Teichmann space or compact surface, you would take the integral over a fundamental domain, but here in the universal Teichmann space, you don't have that. So it's really the Weil-Petersson symplectic form here. Well, in finite dimensional case, why these two are the same is also, I find, very magical as well. But, yeah.
So in some sense, your very triangulation is like an infinite Pann's decomposition.
Yeah. But they're not independent, so I'm not totally sure like how one can interpret this. Yeah, how much time I have? I have 15 minutes. Okay, I should probably give you, I think that's the end of my slides. Or I promised you something in number theory. Let me just do this.
Why don't we put the fairy tessellation up? That's good.
No, I like it. I'm proud of myself about this. I should turn off the. Anyway, I have this is the main theorem. Let me just do one implication for you. Right, I'm going to show you C1 alpha. So if log of phi prime is inside C alpha with alpha strictly larger than 1/2, then theta is in L2. So this of, let's show you this. All right, the first one you can give already to your calculus student. So if my log of phi prime is C alpha, so at least my phi is C1. It's very nice. So if you look at here, this would be something like log of phi prime at the point in between A and B. Right, this I have a 1/2. So there are the same number of them. Well, so this first of thing, we get that theta of E, so E is an edge, right? This is will be less or equal to a constant times the length of E to the power alpha. So the length, I mean, so this is my edge E. The length is this is the length of E, Euclidean length. Okay, the second part, well, in order to show theta is in L2, I need to show that if I sum up the length E to the power 2 alpha, for all the E in the Ferri tessellation, this has to be finite. All right, okay, so first of all, if this is 1, it's just a 1, it's going to be infinite. Because at each generation, I have a sum of the whole length of the circle. Right, the infinite generation, I'll get infinite. So it's definitely not true for 2 alpha equals 1. But here, my alpha, 2 alpha is strictly larger than 1. Okay, let me do the first thing, because it's so nice in the upper half plane. I will just look at one quadrant. I just look at this part. The edges contained inside this part. So this will be going to map to 0 and 1. Right, you have the edges. This map to from the disk to the upper half plane, this Lipschitz. It's very nice. So I just need to bound the distance here. Right, and now these are my Ferri tessellation. Here, doing my freshman sum. I'm going to split them into all the rational numbers between 0 and 1. So I pick one point, I say this is P over Q. And I look at all the edges which is with higher generation of it. So for instance here, you'll have these ones. So I split my set of edges according to their lowest generation parent. The parent is the 2 endpoint of the. And what you have is things like, so I will sum over all the child of PQ. Right, all the red edges. So sorry, this is white. Okay, this is white. Okay, okay. Let me say what is this guy. Okay, this guy. Okay. There are some. So this one. Let's say this one. You can zoom in. It doesn't have to be 1 here. Okay. This one I call P prime over Q prime. So what is this guy here? this guy, the first guy will be the freshman sum, Q prime plus Q. The next guy will be the freshman sum of this guy and this guy. So we get P prime plus 2P, Q prime plus 2Q. Right, you see how it goes? So this will be, the distance will be all the P, Q minus, I will just take n larger than 1, minus P prime plus n P, Q prime plus nq to the power 2 alpha. Okay, so this thing here, I can expand it. This will be just Q times Q prime plus nq. On the numerator, because this is an edge, its determinant is 1. Okay, 2 alpha. This thing is less or equal to 1 over q to the 4 alpha, 1 over n to the 2 alpha. I will continue here, my calculation. So this was less or equal to sum of all the p over q, less or 0 than 1. Now I sum over all the n. I see zeta of 2 alpha, q to the 4 alpha, zeta of 2 alpha. Well, here now we have to sum over here. How many p I can choose, which is between 0 and 1? Well, there are at most q of them. You can do more precise, but let's do freshman. So this will be less than sum over all the q larger than 1. You just get the 1 over q 4 alpha minus 1 zeta 2 alpha. This is equal to zeta of 4 alpha minus 1 zeta of 2 alpha. This is finite. This is finite. Yeah. So that completes the proof. Yeah. So somehow the story is as following. Like with Catherine, we were thinking about this question. I say, okay, Fairy tessellation number series have been looking at it so much, and we search online, and we found papers about Fairy sequence where they take the length to the power 2, 3, 4, 5. But no one look at fractional and say, okay, this must be really difficult. And then until one day we went to a beach and in San Francisco, and there's no internet. We were trying to search for some advanced number theory, and we couldn't find the internet. And we decided, oh, let's do it ourselves. Yeah, but I think number theorists care more a different question, because I think they look at Fairy sequence, they usually take the upper bound on the denominator. It's not like the generations that we do. So I think that those papers are still very, very interesting for different reasons. But for this one, we interested particularly is actually very simple. Yeah. So this is this inclusion we proved just now. For this inclusion, we in fact construct the explicit quasi-conformal map using these shears and show mu is to be L2. So we have it. For this one, we also had to use some control on the cross ratio for Weil-Petersson homeomorphism. I'm not telling more, but why these inclusions are not strict. Right? For instance, here, this is not exactly the same, because remember, for h, it implies the derivative at the rational function, and that rational points is well defined. But for Weil-Petersson, it's not always the case. You just have the derivative is in h1 half. h1 half doesn't mean it doesn't see anything about rational numbers. So they're strict, and yeah, we don't really know how to improve it. Maybe one can do something a bit more artificial. You rotate a bit, and then, but it doesn't seem to be so pretty anymore. Yeah, okay. Let me just stop here. Thanks for your attention.
So we can all take a question, but before, let me share with you something I learned this morning. So the talk was recorded. The answer to your question will be recorded, but for posterity, it's better if your question is recorded as well. So if you raise your hand, please wait for me to bring the microphone.
How big is H in the Weil-Petersson? Like, hey, can you approximate Weil-Petersson?
Yeah, that's a very good question. So depending on which topology that you take, right? In H, there's a natural L2 metric. It's L2 space. So this is complete for itself. This L2 metric, we can show that if you're converging, that convergence in L2 is much stronger than Weil-Petersson. But if you ask about using the metric on Weil-Petersson, this will be dense, because already C1 alpha is dense in WP. So in other way, here we can also, from this, we obtain that the piecewise Möbius circle homeomorphism, they're naturally here. They're already dense in Weil-Petersson. Yeah.
Other questions? Yes.
So you get piecewise Möbius maps.
If you have finite split,
yes. Yeah. Can you characterize piecewise Möbius transformations with integer coefficients? Piecewise SL to Z. You know the Thomson group?
Yes. Right. I think this is it's very interesting, because in the Ptolemy group, right, Thomson group, is also obtained by doing flips on the diagonals. I think that if you have, so every time, okay. So if I do flip here, and this is not anymore fairy, but it is a tessellation, so it corresponds to a map which would send these points. Now you have to send these points are fixed, but you will have to send this point to this point. So I think this is what Penner already showed, that you can get the Ptolemy group by doing at least in the finite piecewise Möbius case. Yeah, I'm not totally sure, but I think it's probably good to look into Penner's. Yeah. Right.
Other questions?
So this is kind of a meta question, which is, how crucial is it that you're actually using the fairy tessellation? Like, are there, I mean, it seems, is it an artifact? Is it just a good way of thinking, or could you use some other kind of tessellation of the hyperbolic plane?
Right, okay, that's a good question. So, you can start with an element in other tessellation. So here, because of the shear, so theta is a linear combination of shear, so I'm just going to explain for shear. If you add two shears, S1, S2, what it does is that using S1, you shift around already by S1. When you're adding S2, you shift further, right? So this S2, what it does is you start from this tessellation, which is a result of the S1 shear. So there you can, you do the thing. So from this, because in terms of shears, like H is a linear space. If you start with any tessellation coming from the H, you can still shear by something like in H. It's staying in H. Yeah, but for instance, if you start something which is not in H, really bad, and then you look at what is L2 shear to be Weil-Petersson, it's not guaranteed to be in Weil-Petersson.
Other questions? Pierre Arnaud was having a question at the very beginning. Do you still have this question? Oh, okay.
The question was immediately answered before I had time.
Oh, sorry, I didn't see you.
Okay, if not, let's thank the speaker again.